Now we're going to count some of these permutations. Remember, these are the permutations, so every time we'll be using up all of the input numbers, or having the same number of blanks to fill as there are numbers that we have to use, digits. So that means if you say the number of permutations of the numbers 1 through n, the set 1 through n, is n factorial. That little n in square brackets is shorthand for the set 1 through n. So we'll probably use that a few times here and there. Faster to write it than with the dot dot dots. So now we add some requirements. So the number of permutations, again, of 1 through n, such that phi of 2 equals 2. So phi is the name for the permutation, thought of as a function. So it takes the numbers 1 through n to the numbers 1 through n. It's the same as saying the second digit is 2 in the list. Or, if you draw the picture, it's the same as saying let's put a string from 2 to 2 to show that its output is, the output of 2 is 2. So looking at the picture or the list, what it says is that now there's only n minus 1 choices for 1, because you can't repeat. 2 is given, it goes to 2, so you could put a 1 there. Then there's n minus 2 choices for 3, n minus 3 choices for 4, all the way down to 1 for the last. So what that does is it takes away a little bit of the freedom, and you only have n minus 1 factorial as the answer, the number of permutations such that phi of 2 equals 2. How about the number of permutations of n, the set, such that phi of 2 does not equal 2? Now there's definitely more than one way of doing this one. It's not too hard. You could think about it and come up with the answer a different way. But I decided to show it with subtraction. And it's the same problem as saying what's a pin number where the second digit is not 2, but it's a pin number of length n, and it uses all the digits of n without repetition. Okay, so you start out with the total allowed, n factorial, and then look at the number of ways to do a permutation where phi of 2 does equal 2. Well, that's the one we just did, so I subtracted off. So that's what I'll get, n factorial minus n minus 1 factorial. And then you can have 2 rules not to break. So yeah, that's why it's in chapter 6, because we're still doing inclusion exclusion. So how about the number of permutations of 7? I'll narrow it down, or nail down a number there instead of using n this time. And such that phi of 2 does not equal 2 and phi of 2 does not equal 3. So 2 things it can't be. So I'll do 7 factorial. That's the total. Then phi of 2 does equal 2 6 factorial ways. That is the one we just worked out above. And here I drew the picture again with 2 going to 2. Then you have 2 going to 3. That's not allowed. We need to subtract those. So again, there will be 6 factorial ways to do that. That's because if you think about it, there's going to be 6 options left to send 1 to, since 3 is taken. Then there will be 5 options left for sending 3 all the way down to the last one. There will only be 1 option left, since 2 to 3 is given. So minus 6 factorial again. And then next we usually have to add back in the intersection. That would be, the intersection would be where phi of 2 does equal 2 and phi of 2 does equal 3. So I drew a picture of that. Phi of 2 is equaling 2 and phi of 2 is equaling 3. So there's a string going to both. But that is no longer a function. You can't send, a function can't send the one input to 2 different outputs. It's like the vertical line test. Basically, a function always has exactly 1 output for every input. So there's no permutations with phi of 2 equals 2 and 3. So that last piece would just be adding back in a 0. And that comes out to 3600.